Myself, Sanmugsundaram, Professor, Sri Ramakrishna Engineering College. In this video presentation, I will be discussing about AC circuits. Outline of this presentation. In this presentation, concepts of RLC circuits are discussed and the problems are explained. And concepts of RLC series circuits are discussed and their problems are explained. Let us consider a pure resistance is connected across a supply and the voltage V is Vm sin omega t, and in this circuit current I is flowing. So an example for pure resistor is carbon resistor. So here the applied voltage is Vm sin omega t and the current is V by R, which is nothing but Vm sin omega t divided by R. So this Vm by R indicates the maximum value of the current. So here small v, small I, they represent instantaneous values. Now we'll see the waveforms. So current and voltage waveforms is shown in this figure. So here we find that both current and voltage are in phase, means the voltage positive cycle starts from this instant and reaches maximum at this point 90 degree and it is completed at this point and negative cycle continues. Similarly, the current also positive cycle starts from here, reaches maximum value and ends at 180 degree and negative cycle continues. So there is no phase difference between voltage and current. So in this case we say that both are in phase. So here coming to the phasor diagram, the phase angle between the quantity is shown in the phasor diagram. So here the two lines are parallel. The voltage phasor and current phasor, they are drawn parallel. It means that they are in phase. There is no phase difference between voltage and current. They are in phase. And coming to the equation for power, power is nothing but product of V into I. These two are instantaneous values. And the maximum power occurs when voltage becomes maximum, current becomes maximum. So it is given by the product of Vm and Im. Coming to the average power, it is indicated by capital P, which is nothing but Vrms into IRMS. Vrms can be simply written as B. IRMS can be simply written as capital I. So the capital letters always indicates RMS values. So this in turn will be equal to I square R. Also this will be equal to B square R. So these formulas already we have used in DC circuits. Same thing is applicable in AC also. Coming to the waveform. So here this is the instantaneous power. It shows how it varies with time. So it starts from 0, reaches maximum when both current and voltage are maximum and again becomes 0 and the next cycle starts. So here this dashed line indicates the average power. So a pure resistor in AC circuit behaves in exactly the same way as in the equivalent DC circuit. And let us see this example. Calculate the power dissipated by a 560 ohm resistor when connected to a voltage source V is equal to 35 sin omega t volt supply. So Vm is 35 and omega is 304 and the resistance value is 560 ohm. So these are the values given in the problem. So you are asked to find the power dissipated in the resistor. Try to remember that the resistor will consume power. So the power in turn will be dissipated in the form of heat. So the RMS value of voltage V is So you know the relationship between Vrms and V maximum for a sine wave. It is Vrms equal to Vm by root 2. So this can be written as 0.707 Vm. So substitute Vm and get the value of Vrms. Similarly, the equation of power is V square by R. Since the voltage is known, can use this formula V square by R. Substitute the values, we get power as 1.09 watts. The unit of power is watts. Coming to the pure inductance. The pure inductance is one which has only inductance. There is no resistance and no capacitance. Ideally, we cannot get an ideal inductor. But examples for inductors are choke coil, transformer winding, motor winding. These are some of the examples. So let us consider the inductance is connected across a voltage source V and current is flowing in the circuit. So here E is the EMF induced in the inductance. When current is flowing, it will produce flux, and this flux again will be linking with this coil, and because of this flux linkage, EMF will be induced. This EMF will be opposing the current in the flowing through the inductance. So here the voltage will lead the current by 90 degree, or in other words we can say that current will lag the voltage by 90 degree. So figure 1.6 shows the voltage and current waveforms. So here the current cycle starts from omega t equal to 0 and ends at 180 degree, and the negative cycle is continuous and ends at 360 degree. So if you see the voltage waveform at omega t equal to 0, its value is maximum. And if you are going to extend this backwards, so the positive cycle will start at 90 degrees before omega t equal to 0. That is somewhere here. So here we find that voltage is leading the current by 90 degree, or current is lagging the voltage by 90 degree. So this is shown in the phasor diagram. So in the phasor diagram, you can see here current and voltage phases are marked and their angle is shown as 90 degree. So here the voltage phasor makes an angle of 90 degree with respect to current in the anti-clockwise direction. If the angle is measured in anti-clockwise direction, then we say that voltage leads the current by 90 degree. In other words, I can also say that the current makes an angle of 90 degree in the clockwise direction. In this case, I can say that the current lags the voltage by 90 degree. So both imply same. So coming to the power waveform is shown here by a dark line. So during the first quarter of the cycle, so the power wave is a positive cycle, and during the next quarter of the half cycle, so it has a negative cycle. During the first quarter of the half cycle, so here the energy will be stored in the inductor, and during this negative cycle, the next quarter of the half cycle, this power or energy will be supplied back to the source. So an inductor will not consume power, therefore average power consumed by the inductor is always 0. Only it will store energy and it will dissipate, or it will supply back to the source in the next quarter of the cycle, and this cycle gets repeated. Coming to the inductive reactance, so here the quantity which opposes the flow of current in the inductor is called as inductive reactance. Inductive reactance is defined as the opposition offered to the flow of AC by a perfect inductor. It is measured in ohms and it is indicated by XL. I told you already that So the induced EMF will be opposing current, but we are not going to express the opposing quantity in terms of EMF. So it is inconvenient to express the opposition quantity in terms of voltage. That is why here we use this quantity called as inductive reactance as the quantity that opposes the flow of current. So this XL is directly proportional to the frequency. So let us see the expression for XL. So the XL expression is XL equal to omega L. So omega is angular frequency radians per second, which will be 2 pi f into L. So let us see how to get this equation. So we can write the EMF induced as minus L into d by dt, where we have seen that the induced EMF has opposite polarity that of the applied voltage. Therefore, E can be written as minus V. So therefore, in the place of E, if I substitute minus V, then I get V equal to L into di by dt. So now substitute I is equal to Im sin omega t. So you differentiate with respect to t. So you get equation for V as omega L Im cos omega t. So this value becomes maximum when cos omega t equal to 1. So when cos omega t equal to 1, so the voltage becomes V maximum. So therefore V maximum is omega L Im. Suppose if you want to get the inductive reactance, divide Vm by Im. This will also be equal to Vrms divided by Irms. So this will be equal to omega into L, and its unit is ohms. Therefore, this is denoted as XL. XL is inductive reactance. It is omega L, which is nothing but 2 pi f L. So omega is 2 pi f. So here you can see the relationship between XL and the frequency. So here it linearly varies with frequency. So since it is frequency dependent, XL increases with frequency. So coming to the example, a pure 20 millihenry inductor is connected to a 30 volt supply. Calculate A, the reactance at this frequency, and B, the resulting current flowing in the circuit. The values given in the problem are L is 20 millihenry and supply voltage is 30 volts and frequency is 50 hertz. So now if you want to find the reactance, you have to use this formula 2 pi FL, substitute the values, so you'll get this value 6.283 ohms. Then the second part is find current. I is nothing but V by XL. So divide voltage by the inductive reactance, you'll get this as 4.77 and its unit is ampere. Example 3. A coil of inductance 400 microhenry and of negligible resistance connected to a 5 kHz supply. If the current flowing in the circuit is 50 milliampere, determine the supply voltage. So the given values are inductance is given, frequency is given, the current in the circuit is 15 milliampere. You are asked to find the supply voltage. How will you find supply voltage? So here, since inductor is directly connected across the supply, the voltage across the inductance is nothing but the supply voltage. So the voltage across the inductance is I into XL. So your I into XL gives you the voltage across the inductance, which we also will be the supply voltage. So first to find XL is 2 pi FL, substitute all the values, get the value of XL, it is 12.57 ohms. So now find out V is nothing but I into XL. So the product gives us 188.5 millivolt. Then let us consider a pure capacitance. When a pure capacitance is connected across a supply voltage V is V sin omega t, and the current I is produced in the circuit and the capacitor is having charge Q. So charge on the capacitor is directly proportional to the potential difference across the capacitance. So here in this case, the current will lead the voltage by 90 degree, or voltage will lag the current by 90 degree. So coming to the waveforms, you can see here both voltage and charge, they are in phase. Charge is is proportional to the applied voltage, whereas current at omega t equal to 0, voltage is 0, but whereas current is maximum. So if we extend this backwards, somewhere 90 degree before omega t equal to 0, so it will be 0. So the positive cycle starts somewhere here at 90 degree before this point. So here I can say that the current is leading the voltage by 90 degree. This is shown in phasor diagram. In the phasor diagram, you can write, if you take voltage as reference, so this current makes an angle of 90 degree in the counterclockwise direction. Therefore, current leads the voltage by 90 degree. In other words, we take this current as a reference, then I can say that the voltage makes an angle of 90 degree with respect to current in the counterclockwise direction. As I said, in this case, current leads the voltage by 90 degree. In other words, I can also say that voltage lags the current by 90 degree. So in inductor, you know that the energy is stored in the form of magnetic field, whereas in the capacitance, energy is stored in electric field. So during one quarter of the cycle, the energy is stored in the capacitor. During the next quarter of the cycle, so the energy is delivered back to the source. The average power consumed by the capacitor is 0. Therefore, a perfect capacitor dissipates zero power. It means that it will not consume any power. So coming to the power waveform, you can see here during the first quarter of the half cycle, so power has positive cycle, the energy is stored in the electric field, and during the negative half cycle, this is delivered back to the supply. And in capacitive circuit, right, the quantity which opposes the flow of current in the circuit is called as capacitive reactance. It is expressed in ohms. It is denoted by Xc. Let us see how to get the equation for Xc. Xc is 1 by omega c, that is 1 by 2 pi f into c. F is the supply frequency. So here we can write charge as V into Qc. If differentiate with respect to t, we get dq by dt equal to c into dv by dt. C is the constant. So what is dq by dt is current. So I can write I is equal to c into dv by dt. What is V? V is Vm sin omega t. You substitute differentiate with respect to t, you get omega Cm cos omega t. So at omega t equal to 0, this value becomes maximum. So the current becomes I maximum when omega t equal to 1. So therefore, Im is omega c Vm. So get the ratio of Vm by Im. Also, this will be equal to V by I. This will in turn equal to 1 by omega c. So find Xc. Xc is nothing but 1 by omega c. So this is nothing but 1 by 2 pi Fc ohms. So this is the expression for capacitive reactance. So here we'll see this problem. A 0.47 microfarad capacitor is connected to a 25 volts, 200 hertz supply. Calculate the current flowing in the capacitor. So the data given the problem is C is 0.47 microfarad, and voltage is 25 volts. This is the supply voltage and supply frequency is 200 hertz. So the capacitive reactance is 1 by 2 pi Fc. So you substitute all the values. In the place of frequency, you substitute 200 and capacitance 0.47 microfarad. So 0.47 into 10 to the power of minus 6 is for 0.47 microfarad. So now get the value of Xc. It is 1.693 kilo ohms. Then compute current. Current is the ratio of V by Xc, which will give you 14.77 milliampere. Next, when we move on to RLC circuits, we'll find the combination of resistance and inductive reactance, resistance and capacitive reactance, or we find resistance, inductive reactance, capacitive reactance in these circuits. So here in these circuits, the opposition quantity which opposes the flow of current in the circuit, in the RL RC or RLC circuit, we call it as impedance. Impedance is nothing but the ratio of V by I to supply voltage divided by the current in the circuit. Now let us consider inductance and resistance series circuits, or are also called as RC series circuit. A pure resistor and inductor, they are connected in series. R and L, they are connected in series, and they are connected across a supply frequencies F hertz, and current I is flowing in the circuit. VR is the voltage across the resistance, VL is the voltage across the inductance. Now we will see the expressions for these quantities, and we will see the waveforms and phasor diagram. So coming to the phasor diagram, so here the voltage VR, voltage developed across the resistance, will be in phase with current I. So the phase difference will be 0. That is why they are parallel lines. Now VL, this voltage across inductance, it will lead the current by 90 degree in the case of inductance. So here it is drawn at an angle 90 degree with respect to current I. So this, it is measured, angle is measured in the counterclockwise direction. So the vector addition of this real component and imaginary component, that is horizontal component, vertical component, the resultant vector is V, supply voltage. So therefore we can write V as VR plus J into VA. And the phase angle between voltage and supply current, we call it as phi. Phi is the phase angle, and whereas cos phi is called as the power factor angle. Cos phi is called as power factor. Coming to the voltage triangle, so only voltages are shown here. So VR is the horizontal component and VL is the vertical, this vertical component shown here, and the vector addition of these two components gives the resultant voltage. V is the supply voltage. So here the phase angle between voltage and this horizontal component VR is phi. Phi is the phase angle of the circuit, and whereas the power factor is cos pi. So from the voltage triangle, we can write V as VR plus J VL. This is vertical component, this is horizontal component. So in polar form, it can be written as V equal to magnitude of this. Magnitude of this is VR square plus VL square under root, that is written here, and phi is the phase angle. So in polar form, we write magnitude at an angle. So here this is magnitude is under root of VR square plus VL square at an angle phi, where phi is the power factor angle. So phi is tan inverse of VL by VR. So phi is, you know that tan phi is opposite side by adjacent side. So that is in voltage triangle. In voltage triangle, the opposite side is VL and adjacent side is VR. So we can write tan pi as VL by VR, pi as tan inverse of VL by VR. And considering the impedance triangle, we can write expressions as shown below. Impedance Z will be equal to this horizontal component plus J times the vertical component. So try to remember, this vertical component makes an angle of 90 degree with respect to horizontal component in the counterclockwise direction. So in the polar form, Z can be written as a magnitude of Z at an angle phi. So magnitude of Z is R square plus XL square. So angle phi. Phi is nothing but the phase difference between the voltage and current. So here phi is written as tan inverse of XL by R. So here phi is tan inverse of opposite side by adjacent side. So voltage across the elements R and L. Voltage across resistance VR is I into R. Voltage across inductance is VL, that is I into XL. Whereas the total voltage is called as V is nothing but supply voltage will be equal to I into Z. Z is the total impedance of the circuit. And here this waveform is power triangle. Here the RL, RC and RLC circuits have three powers. That is real power. This is the actual power consumed by the circuit. Usually in RL, RC, RLC circuit, the resistance is the component that will be consuming power. So real power. This is utilized power, and the vertical component is reactive power. It is denoted by capital Q, and the vector addition of these two powers is apparent power S. So apparent power is product of V into A, volt ampere, and real power P is VI cos pi, and reactive power is VI sin pi. So we can write the equation in rectangular form as P is equal to, that is S is equal to P plus J. So from the voltage and impedance triangle we can write cos by S or by Z. This is from impedance triangle. So cos by S, adjacent side by hypotenuse. Adjacent side is resistance, hypotenuse is Z. From voltage triangle we can write cos by S V or by V. Similarly sin pi from impedance triangle we can write it as opposite side by hypotenuse, that is XL by Z. From voltage triangle we can write it as VL by V. Tan phi S, opposite side by adjacent side XL by R. From voltage triangle VL by R. And the phase angle, for example, if you know cos pi equal to R by Z, so you can find phi as cos inverse of R by Z. So where R is the resistance, Z is the total impedance of the circuit, consider only the magnitude. So from the power triangle, right, we can write the following equations. So real power, which is also called as true power, or this also will be equal to heat dissipated in the resistance. So this power is VI cos pi. So voltage, supply current, and cos pi is the power factor. So this is I. This also will be equal to I square R, the power dissipated in the resistance. Reactive power denoted by Q. Q is VI sin pi. Its unit is volt ampere reactive. Apparent power, it is denoted by S. In rectangular form we can write it as the vector addition of real power plus reactive power. So the apparent power S can be written as P plus JQ. P is the horizontal component and Q is the vertical component. In polar form it can be written as S is equal to magnitude of S phase angle phi. So this can be written as P square plus Q square under the root. This is magnitude and at an angle phi. So phi is nothing but the phase angle between horizontal component and hypotenuse, or between the horizontal component and the resultant vector. So similarly, these expressions can be written from power triangle. So cos pi is adjacent side by hypotenuse, that is P by S, which is nothing but VI cos pi by VA. Sin pi is opposite side by hypotenuse, that is Q by S. This is nothing but VI sin pi by VI. Tan phi is opposite side by adjacent side, Q by P. Q is VI sin pi, P is VI cos pi. So coming to the problem, a resistor of 250 volts is connected in series with a 1.5 Henry inductor across a 100 volt supply. Its frequency is 50 Hz. Calculate the current flowing in the circuit. B, the circuit phase angle. C, the power factor. D, the potential difference or voltage developed across each element. E, the power dissipated or true power or real power. Then F, reactive power, and G, apparent power. So given data are resistance value is given, inductance is given, supply voltage is given, supply frequency is given. So the circuit is shown here. So here 250 ohms is connected in series with 1.5 Henry. So current I is flowing in the circuit, and 100 volts 50 Hz supply is connected across the circuit, and VR is the voltage across the resistance, VL is the voltage developed across the inductance. So as to find the various values. So first we have to find the current flowing in the circuit. The current flowing in the circuit will be V by Z. You have to use this formula. Then whether we know Z is nothing but impedance of the circuit. It is not known. So we have to compute the impedance. Impedance is given by the formula under the root of R square plus XL square. So R is given whereas XL is not given, but inductance is given. So you have to find XL, inductive reactance. It is 2 pi FL. F is frequency, L is 1.5 Henry. So find F, XL, then impedance, then find current. So this gives you 187.5 milliampere. So this is the RMS value of current. Then coming to the phase angle phi. So phi, since we know resistance and impedance of the circuit, you can use this formula cos inverse of R by Z. So if you substitute the values, you will get the phase angle as plus 62.05 degree. This value phase angle can be expressed in degrees or in radians. If you want to express it in radians, you multiply this value by 3.14 and divide by 180 degrees. So you get 1.083 radians. So power factor is cos pi. So cosine of the angle phi. So cos of 62.05 is 0.47. So you have to write here lagging or leading. So if the current lags the voltage, you have to write lagging. For inductive circuit, you have to write lagging. For capacitive circuit, you have to write leading. Then voltage across elements. Voltage across resistance VR is product of I into R. Substitute the values, will get 46.88 volts. Voltage across the inductance is VL. So VL is product of I into XL. Substitute the values, will get 88.35 volts. Then power dissipated in the resistor, or this is also called as real power or true power, is denoted by capital P. Capital P is I square R. Use this formula RVA cos pi. I square R, this formula, substitute the values, you will get 8.78 watts. Or if you use this formula, substitute all the values, you will get 8.78 watts. So you can use any one of the expression. So this is actually the power consumed in the resistance. Coming to the reactive power Q. Q is nothing but VI sin pi. So V, this is I, and sin of, already we know the angle. You substitute the angle, so you'll get 16.56, where VR stands for volt ampere reaction. And the last one is G, apparent power S. S is product of V into I. So multiply voltage with current, you will get 18.75 volt ampere. So here all the values are indicated in this voltage triangle. So voltage VR is 46.88 volts. And the vertical component VL is 88.35 volts, and the vector addition gives you the resultant vector as supply voltage, which is equal to 100 volts, and the current magnitude is 0.1875 ampere. So let us consider this problem. Here, coil of resistance 35 ohms and inductance 0.02 Henry carries a current of 326.5 milliampere. The current is shown here. When connected to a 400 Hz AC supply voltage is 400, determine the supply voltage. So how will you find out the supply voltage? So supply voltage is given by the formula I into Z. So if you know impedance, you can calculate this voltage. But we have to calculate the inductance. If you want to calculate the inductance, we have to know R and XL. R is given in the problem, but XL we have to find out. So find XL, use this formula 2 pi FL, find the value, 15.27 is the value. Then find impedance is set, it is 61.25 ohms. Then find out the voltage, multiply current with this impedance, this gives you 20 volt. So 20 volt is the supply voltage. We'll see the next problem. Two separate tests were carried out on the coil. Two tests are conducted. First test, DC supply of 20 volts is applied and it is found that 2 ampere is flowing through the circuit. The second test, it is connected across a 24 volts 200 Hz AC supply. In this test, it is found that the current flowing is 1.074 ampere. You have to calculate the resistance and inductance of the coil. So here, first test only DC voltage is applied. So if DC voltage is applied, the frequency for DC voltage is 0. Therefore, the inductive reactance also will be 0, because since it is formula is 2 pi FL, L is 0, therefore XL is 0. So in DC circuits, inductance will not be having inductive reactance. So it will be circuit will be having only resistance. Therefore, we can find resistance from the first test by dividing the voltage, applied voltage, by the current in the circuit. So we'll get 12 ohms. Next, when it is connected to AC supply, right, then there comes impedance of the coil. So we will have inductive reactance and impedance. So from the given values, that is voltage and current is given in the second test. Therefore, we can find impedance. So calculate the impedance by substituting the values. It is 22.35 ohms. But from impedance, we have to find out this inductance L. So to find out inductance L, first we have to find out XL. So use this formula, Z square equal to R square plus XL square. So XL is under the root of Z square minus R square. Z is known, R is known. So find XL, it is 18.85 ohms. So from this, equate this XL to 2 pi F and find out inductance L. L will be XL by 2 pi F. So substitute all the values, you will get this value as 15 millihenry. Next, capacitance and resistance in series. So let us consider the circuit. So resistance and capacitance are connected in series across the supply. Supply voltage is V, F is frequency, I is the current flowing in the circuit, V is the voltage across resistance, Vc is the voltage of the capacitance, and this is the phasor diagram. In this case also, the current and voltage are in phase, and voltage across the capacitance will lag behind this current by 90 degree, and vector addition of VR and Vc gives you the resultant voltage V. V is nothing but the supply voltage. You should remember that in this circuit, if the resistance is very much greater than XC, capacitive reactance, the power factor, this angle will be small. The cos pi, this angle will be small. This vector will move close to this vector VR. The phase angle will reduce. But if XC becomes very much greater than resistance, then this vector will be moving close to this vector, vertical component. So therefore, in that case, the phi will increase. So here, from the voltage and impedance triangle, we can write the following equations. From voltage triangle, VR can be written, that is, V can be written as VR minus JVC. So try to remember that VC makes an angle of 90 degree with respect to VR in the clockwise direction. So here we are writing minus J to VC. So in polar form, it is written as magnitude at an angle, phase angle phi. So magnitude is under root of VR square plus VC square, and the phase angle is phi. So phi is tan inverse of, that is, imaginary component by real component, that is VC by VR. Similarly, from the impedance triangle, we can write the equation for Z as R minus JXC. In polar form, magnitude of Z at an angle phi. So magnitude of Z is under the root of R square plus XC whole square. Phase angle is phi. So phi is tan inverse of, again, imaginary component by real component, XC by R. So these values are same. This phi and this phi, you will get the same value. So voltage across elements R and C. So voltage across resistance R is VR, is nothing but product of I into R. Then voltage across capacitance is VC, it is product of I into XC. Then the total voltage, supply voltage, will be equal to I into Z, where Z is the total impedance of the circuit. Again, from voltage triangle and impedance triangle, you can write the following equations: cos by S R by Z, and it's also will be equal to VR by V, and sin by is XC by Z from impedance triangle. From voltage triangle, it is VC by V. So the vertical component is VC. and tan pi is xc by r. That is vertical component by horizontal component. So here also cos pi, from any one of these expressions you can find phi. So cos pi here I have written as r by z. So again power expressions, real power, active power, apparent power, these equations remain same. There is no change. So this equation also used for RLC circuits. So coming to the problem, a 22 nanofarad capacitor and a 3.9 kilo ohm resistor are connected in series across a 40 volt 1 kilohertz supply. Calculate A, the current flowing through the circuit, B, the circuit phase angle, C, the power factor, D, the potential difference or voltage developed across each component, E, the power dissipated, F, the reactive power and apparent power. So given data are the resistance value is given, capacitance value is given, voltage and frequency is given. So first we have to find out the current. To find out current, we have to use this formula V by Z. To find Z, we have to know R and XC. R is known, we have to find XC. XC is 1 by 2 pi of 6. So find XC, then substitute in this expression, get Z, then substitute Z in this expression, you will get current as 4.87 milliampere. So to find phase angle phi, use this formula cos inverse of R by Z, because R and Z are known. So you'll get angle as minus 61.67. So you find that the angle is minus. It means that the current is leading the voltage vector by an angle 61.67 degrees. So in radians it is minus 1.076 radians. The power factor cos pi, so cos of 61.67 is 0.47, you are right leading. For capacitive circuits, so if the current is leading the voltage by 90 by some angle, then you have to write here as leading. Then voltage across the resistance, VR is product of I into R. Substitute the values, find VR, it is 18.99 volts. Then find out voltage across capacitance, it is I into XC. Sorry, here it should not be inductance, it should be capacitance. So this value comes to be around 35.23 volts. The power dissipated in the resistor or real power, P is I square R, or you can use this formula VI cos pi. Substitute the values, in both cases you get 92.4 milliwatts. Reactive power, use this formula VI sin pi. Substitute the values, so it will be 171.5 milliwatt. Apparent power, it's product of V into I, so you'll get this as 194.8 millivolt ampere. So now draw the phasor diagram and indicate all the values. So here you will find that the voltage vector, supply voltage, makes an angle of 5. In this case it is 61.67 degrees with respect to horizontal component in the clockwise direction. So voltage, supply voltage is lagging behind the current by an angle of 61.67. Next problem. A 470 ohms resistor is connected in series with a 0.02 microfarad capacitor across a 15 volts AC supply. If the current is 28 milliampere, calculate the frequency of the supply and potential difference across the capacitor. So this is a circuit. Sometimes if circuit is not given, we have to draw the circuit. So the resistance and capacitance value is given. Voltage across the capacitance is VC, we have to find out. And the current in the circuit is 28 milliampere. Supply voltage is 15 volts. You have to find out frequency. So first we have to find out the impedance. So from impedance you can find XC. From XC you can find out frequency. Then we can find out voltage across the capacitance. So voltage across the capacitance, we have to use this formula I into XC. So to find Z, we divide V by I. So V and I are given, so you'll get 535.7 ohms. Then find XC, it is nothing but under root of Z square minus R square. This comes to be around 257.08 ohms. Then you know the formula for Xc is 1 by 2 pi Fc. So here the only unknown is frequency. So find frequency. So it comes to be around 30.95 kilohertz. Then second part, find Vc, product of I into capacitive reactance, that is comes to be around 72, that is 7.2 volts. Then we'll come to the last part, that is RLC series circuits, resistance, inductance and capacitance in series. So let us consider this circuit. All the components are connected in series. Resistance, inductance and capacitance are present. Voltage across resistance VR, voltage across inductance is VL, voltage across capacitance is VC. Supply voltage is V, frequency is F, and current I is flowing in the circuit. So try to remember that in this circuit, the current and this voltage will be in phase. Always the resistor voltage and the current will be in phase. Whereas in the case of inductor, VL will lead the current by some angle. VL will lead the current, or current will lag this voltage by some angle. In the case of capacitance, current will lead this voltage by some angle. This current will lead this voltage by some angle. So here the net reactance will be the difference between the two reactances. Suppose XL is the reactance of this inductance, XC is the reactance of this capacitance. The net reactance will be XL minus XC. Suppose if XL minus XC is positive, then inductive reactance is more than capacitive reactance. The same circuit will behave like an inductive circuit. In inductive circuit, you know that the current will be lagging behind the voltage by some angle. In the other case, if XC is greater than XL, then the circuit will behave like a capacitive circuit. In this case, the current will lead the supply voltage by some angle. Coming to the phasor diagram, so here let us assume that VL minus VC is positive, that is XL is greater than XC. So here VL minus VC, it is drawn here, it is taken as a positive value. Otherwise, if this value is negative, then we would have drawn this vector in this pointing downwards. So now VR is the voltage across the resistance. So this vector addition, VR plus this voltage, the voltage difference between VL and VC. So these two vectors addition gives you the supply voltage, and the phase angle is nothing but the angle between supply voltage and current. Coming to the impedance triangle, so where horizontal component is R and vertical component is XL minus XC, if XL is greater than XC. So if XC is greater than XL, then you have to draw it downwards. So the resultant, the addition of these two phasors gives us impedance Z. So the phase angle between Z and R component is phi. So coming to the equations again from the impedance triangle, you can write the following equations. Cos pi is adjacent side by hypotenuse R by Z. Sin pi is opposite side by hypotenuse, that is opposite side by XL minus XC by R. We have to consider only the magnitude. Tan phi is opposite side by adjacent side, that is XL minus XC by R. So coming to the impedance in rectangular form can be written as R plus, for inductive reactance we have write plus JXL, for capacitive reactance we have write plus minus JXC. So this in turn can be written as R plus J into XL minus XC. So the magnitude we can write Z square as R square plus XL minus XC whole square, or the magnitude of Z will be under the root of R square plus XL minus XC whole square. This is the equation for impedance. Coming to the voltage across the different elements, voltage across resistance is a product of I into R, voltage across inductance is product of I into XL, product of, that is voltage across VC is I into XC, voltage across the supply voltage is I into Z. Z is the total impedance of the circuit. So coming to the problem, a coil of resistance 8 ohm and inductance 150 millihenry is connected in series with a 100 microfarad capacitor across a 240 volts 50 Hz supply. Calculate A, the circuit current, phase angle. C, the potential difference across the coil. D, the potential difference across the capacitor. E, the power dissipated in the resistor, or also called as true power. F, reactive power. G, apparent power. Given data are that coil is having resistance and inductance. So the coil has resistance of 8 ohms and inductance as 0.15 Henry. And capacitance value is given. You're asked to find the voltage across the coil. So voltage across the coil will be I into the impedance of the coil. So for calculating the impedance of the coil, only you have to consider this resistance and the inductive reactance of this coil. Then the capacitance value is 100 microfarad. So you have to find voltage plus the capacitance also. Now we'll see how to find out the values. First we'll find out the current in the circuit. To find out current, we have to use the formula V by Z. So Z is nothing but impedance of the circuit. We have to use this formula R square plus XL minus XC whole square. So what about XL and XC? So we have to find out. So find XL is 2 pi FL. So it comes to be 47.12 ohms. Then find out XC. It is 1 by 2 pi FC. It comes to be around 31.83 ohms. Find impedance, then find out current as ratio of V by Z. This comes to around 13.91 ampere. Then second part, find phase angle phi. So use this formula cos inverse of R by Z. So Z is no, so we can use this formula. The angle comes to be around plus 62.38 degrees. In this case, since the inductive reactance is greater than the capacitive reactance, so here the current will be lagging the voltage by some angle. So therefore here we have to write angle as lagging. Then to find out the voltage across the coil, you have to consider only inductance and both the resistance and inductance of the coil. So use this formula. Impedance of the coil is under the root of R square plus XL whole square. So this is XL is impedance of the coil. It is reactance of the coil. So this is given by 8 square plus 47.12 whole square. This comes to be around 47.8 ohms. Then voltage across the coil will be the product of I into the impedance of the coil. So you multiply current with the impedance. This comes to be around 664.9 volts. To find out voltage across capacitors, multiply current with XC. This comes to be around 442.8 volts. Then next part is power dissipated in the resistor, capital P, which is also called as true power or real power. The formula is I square or VI cos pi. So substitute values, you'll get both cases, you'll get 1.548 kilowatts. Then reactive power Q is product of VI sin pi. So substitute all the values, we'll get this value as 2956 var. So we can also write in terms of kVAr. So divide this value by 1000, so you can write it as 2.956 kVAr. Then apparent power is product of V into I. Substitute the values, will get 3.338 kVA. Here please remove this, K equal to should be removed here. So and here the impedance diagram of the coil is shown here. So this is the resistance, horizontal component, vertical component is inductance of the coil. If you add these two, you will get impedance of the coil. And this is about AC circuits. I hope you have understood the concepts of R, L, C, RL, RC and RLC circuits, and also you have understood the problems. Thank you.